everything on this slide, this is it. This was our goal. We were working towards everything that we're going to do really in 2 and 3. All those little pieces we learned along the way, dividing, whether it's a factor or not, rational zeros theorem, so we could test specific numbers and everything else, all kind of leads us down to this idea that we can now factor any polynomial, well, not any, but most every polynomial that we'll see, okay? Now, we hadn't exactly done one like the first one because this one has an imaginary root in it. We've done them with real numbers, and it works the exact same way. This one's a little bit tougher, but we're going to work through all of these and kind of see culmination of everything. So first problem, 4th degree polynomial, and it has roots of 3i, 6, and 2. Don't worry about the point yet. We'll talk about what the point does in just a second. So first thing with that, this is a 4th degree polynomial. So how many, and I have an imaginary root here. So how many roots should it have since I'm listing imaginary? It should have 4 of them, but I only give you 3. Because what we're working with here is what's called the conjugate roots theorem. We have real numbers of 2 and 6, and I give you a positive 3i. That tells you what the 4th root has to be, because the positive 3i has to have its conjugate part, which is negative 3i. Anytime you get a complex root that has both the real and the imaginary part, or just the imaginary part, they're going to have a, let's say we had a plus bi. That guarantees that we're going to have a minus bi. And those are called conjugates. And if you look at the one in the notes that we went over that had this on there, that theorem was down there on the bottom as I put that in there. But anytime you're given one of these with roots, if you have one complex root, it means you have another. They always come in pairs. Okay? And all you need to do, this has a 0 in front of it. I don't normally write the 0, so I just kind of left it out. But this one was 0 plus 3i, so the other one had to be 0 minus 3i. So I ended up with 4 roots. Now I want to put this in standard form. So to put this thing in standard form, I take each one of my roots, and I solve it for 0. I put 0 out here on the right side. And that'll tell me what was supposed to go inside the parentheses for each one. So when I solve this, I get x minus 2 equals 0. So this one is x minus 2. This is, they were both positive, yes they were. X minus 6, so that one's x minus 6. I don't get 3 out of the other side. Now remember, we worked with these imaginary and complex numbers before. They work just like real numbers because they are part of what makes up, real numbers and imaginary numbers are also complex. They all work with the same operations. So I just need to minus that to the other side. So this is what would appear in the completely factored. And this one turns into x plus 3i is 0. Now, eventually we're going to have to multiply this stuff out because I need it in standard form. And right now this is partially in factored form. So we always start by writing this in factored form, where I see linear components, all the x's have powers of 1. I see the same number of them as the degree of the polynomial, which I knew it was going to be 4th degree. So I know I'm on the right path. Now we need to talk about dealing with this number, because this number will give us a specific answer, okay? And what happens with polynomials is, you got to think back to when we did transformations. Remember the A transformation? You can put an A transformation in front of this thing, some number up here, and it won't change the roots. It'll just change how tall it is. It'll still make it cross it the same. spot. So what this is doing is this is giving me an X value and a Y value to plug into what I have right here to solve for this A, meaning the X is 3. So what I need to figure out first, because I'm going to solve for this A, I need to put 3 in everywhere I see an X on the right side. So that's 3 minus 2, 3 minus 6, 3 minus 3i, and 3 plus 3i. And you're going to want to find this A value before you multiply everything out. And f of x is another way of saying y. So this side is equal to 18. Now what's going to happen on the right side, all of this is going to turn into just a single number that I'll end up dividing to the other side, and it'll figure out what A is. Because 3 minus 2 is 1. 3 minus 6 is negative 3. Now we've got to go back to when we talked about this before. Those are complex numbers now, and I need to multiply them together. So let's draw the box and multiply these things together and remind ourselves what happens here. So we have 3 minus 3i and 3 plus 3i. So we'll follow that same process we always have. This is 9. Negative 3 times a positive 3 is negative 9, and it has an I. 3 and positive 3i is positive 9i. And negative 3 and positive 3 is negative 9. And I times I is I squared. And what we see here, this middle column cancels out. And that always happens with conjugates. These two will cancel each other out. So we're left with 9 minus 9i squared. But I don't need the I anymore because now it's squared. Anybody remember what I squared equals? Negative 1. So this is negative 9 times negative 1. This is really 9 plus 9. So all of this turns into the number 18. So now I multiply those 3 together. The A on the other side, the way we're used to seeing it. 18 times 3, that's 9 times 6, so that's 54, right? So that's negative 54, A. And now we can solve for A. And I'm just not going to write it with, I'm going to write it the other way. I'm going to go A is 18 over negative 54, just so I have enough space to simplify it. So 18 over 54 is 1/3. Right, negative 1/3. Now what we've solved for at this point, this means that this number in factored form is negative 1/3. And we'll have to deal with that when we go through. So we've now actually got all of our factored form. And let's write that on another slide. So we figured out the factored form for this was f of x is negative 1/3 x minus 2, x minus 6, x minus 3i, x plus 3i. And remember, this is factored form because we can see all of the roots and zeros and factors in it. But we don't want factored form, we want standard form. So what do we do to all those things to find standard form? We got to draw the boxes and multiply them out. So one thing you always need to do with this, when you have a complex root that you're going to multiply, these two will always get multiplied together first as a pair. Okay, so we'll draw our box and we'll multiply those. Because what's going to happen here is the I is going to disappear just like it did when we found the number. Okay, so x minus 3i, x plus 3i. So we get x squared. This is a negative 3xi. They don't go together, they just get listed. This is a positive 3xi. And then negative times a positive for those threes is negative 9, and it's I squared. Now, even though this diagonal is more complex because it's got an x in it, it's also still the same thing with opposite signs. Those canceled out. Just like they did when we had the number down here, where that diagonal canceled out. The reason that the I disappears is because they always appear in conjugate forms. And this middle part that has I in it is always going to disappear. Meaning that what we're left with, this is x squared minus 9i squared. And we know I squared is negative 1, so this is x squared plus 9. So that means when we multiply that together, we got x squared plus 9. Now we need to draw the box and multiply this one just like we normally would. So x minus 2 and x minus 6, that's x squared minus 2x minus 6x plus 12. So this one is x squared minus 8x plus 12. And we still have the 1/3 in front. So all we did is that one step of multiplication. Now we only have one left, okay? Because all we're really doing is we're just multiplying out all this factored form, and then we'll deal with the 1/3. So let's draw this over here. So we're going to put our x squared plus 9 right here, and we're going to multiply that by x squared minus 8x plus 12. Once you get rid of that I, it's kind of back into what you learned back in 8th grade in Math 1 again, okay? And really, it's just be really cautious as you go through like you always would. So we get x squared minus 8x to the 3rd plus 12x squared plus 9x squared minus 72x plus 108. And then we just need to list our answer. Now be careful here, because we didn't put the middle term of 0 in there, the diagonals don't add up anymore. But we end up with, I'm sorry, that shouldn't be squared. I think I said fourth and I wrote squared, because squared times squared is a fourth. X to the 4th minus 8x to the 3rd. Now the squareds need to get put together, so that is 21x squared minus 72x plus 108. So 1/3 x to the 4th minus 8x to the 3rd plus 21x squared 72x plus 108. Now, if you go by the full-on definition of a polynomial, that fraction, to be considered proper, shouldn't be multiplied through. So as you're going through with this, that's technically our answer with the 1/3 common factor pulled out. But if they were to put that back in there, and then again, if you're matching to multiple choice, I won't put the 1/3 back in there, but something else could. Just multiply everything by 1/3. So that's 1/3 x to the 4th minus 8/3 x to the 3rd plus 7x squared, because 21 divided by 3 is 7. 72. Is 72 a factor of 3? Yes, because 90 minus 18, right? That's 24. And 108 is not a factor of 3. I know that. Well, I don't know that for sure. I should probably not assume and go ahead and divide. It is. It's 36. But 72 also is. So these are the same thing. And this is where, you know, comes down to proper, they're both the same number. But you really, the key with this is what I'm looking for you to do is to multiply these things out, however many factors you have, okay? And if you're only given one complex zero, you're guaranteed the other one has to be in there. Those are the two things that we're working with there. Getting rid of the I is the hard part. Multiply those two conjugates together, the I will disappear, and then after that it turns into something that you've seen before much more regularly. All right, let's jump into this factoring problem. Now notice that I didn't ask you to list P over Q or any of that stuff. I just said to factor it. But for something like this, the factoring that we know starts with this P over Q, so we can figure out what to divide with. Between that and looking at the graph. So P is 8. So that gives us plus or minus 1, plus or minus 2, 4, and 8. And this is 1. So this is just plus or minus 1. So if we look at our possible rational zeros, that P over Q list, since everything's just divided by 1, it's just P. So 1, 2, 4, and 8, all with positive negatives. So that should be where our rational zeros lie. Now, for the ones that we're going through, you're going to have some sort of rational zeros to find, okay? So some of these have to work. What's the easiest way to see which ones work? Well, let's look at it and see what we should start with. We had x to the fourth plus x to the third plus 2x squared. X to the third plus 2x squared plus 4x minus 8. So when we talk about knowing whether these things have true, like complex numbers with I in them, we know this is a fourth power polynomial. How many zeros do I see here? I only see 2. It looks more like a squared function that can keep rolling back. I can see the end behavior of those is going to keep taking them up forever. So that means when you think about rule of signs, I know that this answer is going to have two complex in it. So it's getting rid of these rationals so I can get down to the quadratic, so I can use the quadratic formula to figure out what these complex roots would be. So just from looking at the graph, I can see, well, this thing crosses at -2 and 1. So I'm going to start with those two things and make sure they work. You can't ever trust a graph fully because even Desmos can do a bad job with graphing them. So we said it was +1 and -2. So let's start with -2. So we're going to go through our synthetic division here. 1, 1, 2, 4, and -8. That's 1, -2, -1, 4, -8, -4, 8. And no surprise that one worked. So that means, and we saw this from the graph right away, that we have an x-intercept at x equals -2, and its factored is going to be x plus 2 is what we'll see inside the factored form. Let's try the +1. So remember, we only need to use what's left over. So 1, -1, 4, -4. Pull the 1 down, multiply. We get 0. 0 is still 0. 4, +4. Remainder is 0, which is what we were hunting for. So that means that x equals 1 is a factor, like we thought from looking at the graph. X minus 1 is what we'll see inside its factored form. So that's where we started with last week, okay? And normally when we get to this, we'd say, well, let's get to this quadratic and try to factor it, okay? So we've got to look at what's left at this point. X to the 0, x to the first, x squared. I'm left with a quadratic. X squared plus 0x plus 4. Now that we have a quadratic, what we're going to do is we're going to factor this like we factored any other quadratic before. Try a times c and see if we can factor it. There's no need to continue to plug in those numbers, but is it going to factor? It's not going to factor the way that we're used to. And we know that by looking at the graph. We know this thing, if it has 4 roots like it should, and they're all real, we should see it cross that x-axis 4 times and be able to divide those out. But because we only saw it cross twice, we know this has 2 complex roots that we need to find. We can verify this trying to set up the box factoring on this, because we would need the factors of 4 that add together to 0. Are there any factors of 4 that add together to 0? Can't add 2 numbers, positive or negative, and get 0. It doesn't work that way. So what this means is we got to use the quadratic formula. That's where we find our complex zeros. So the quadratic formula is x equals negative b, which is 0, plus or minus the square root of b squared minus 4 times a times c, all divided by 2 times whatever the coefficient of the lead term is, a. And then we can go through and simplify this. So the 0 in front doesn't do anything. So we get plus or minus the square root of 0 minus 16, which is negative 16, divided by 2. So square root of 16 is 4, because let's remember the way that we deal with this. This is negative 1 times 16. The square root of negative 1 is where the I comes from. The square root of 16 is 4. So the square root of that negative 16 is 4i. Still got to divide it by 2, and you don't need to worry about the I here. You just worry about the coefficients. 4 divided by 2 tells you, I lost my plus or minus, I apologize. But these 2 roots are plus or minus 2i. Now what that means, and I'm going to write it over here because I'm out of room. That means our x is positive 2i and our x is negative 2i. Following the same pattern that we did up here, that means in its factored form, we would get x minus 2i for this one and x plus 2i for that one. So we've found all the zeros. Here's all 4 zeros. I'm going to highlight them in red. And right next to it, we listed all the factored forms. Remember, that's that solving it for 0 part. So if we go and we actually list out the complete answer to this thing. Zeros are x equals. Factored form is f of x equals, and we're going to see 4 parentheses for this 4th power polynomial. So we got negative 2 and 1, positive 2i, and negative 2i. So those are the zeros. In factored form, this was x plus 2, x minus 1, because remember we're doing starting with this and we're solving it for 0. Just like we did in the other one when it tells us where they go in. This one was x equals 1, so that's x minus 1. 2i, you got to minus that over. So this is what should be in that parentheses for its factored form. Just like the real number, just like the only real numbers, they don't have an imaginary part. These ones that are complex but only have an imaginary part, they work the same way. This is x plus 2i, 0. So that goes x plus 2i. So here's the zeros, and here is the factored form. It's essentially the same process as last week, but when you get down to your quadratic, instead of being able to easily factor it, you're going to have to use the quadratic formula to hunt out those two imaginary roots, okay? Now, the third one is a little bit different. And we're going to kind of explore this because there's two formulas. Well, there's three formulas that we have to remember when we do this, okay? So we're going to factor this one, but I want to look at the graph first because I want to predict, kind of use Descartes rule of signs in our head. It's got one change each time, okay? But if we go and we graph this thing, so this one is x to the 6th minus, what was it, 4096? Okay. This is what our graph looks like. And it's really hard to even see overall what it looks like. Because eventually you start scanning out and it turns into almost nothing. If I could adjust these axes better, it would look like a parabola. The parabola is just, it's way down on the bottom of the y-axis, or way down on the y-axis for its bottom. The important part of this, though, is how many roots do you see? You only see 2, okay? Now, you can try to do this one with factoring out the P over Q, but the P over Q list is going to be insane because how many factors does 4096 have? I don't know that off the top of my head either, but it's got a bunch, right? I know that the ones that should work are going to probably be -4 and 4, but then when you look at this is you say, well, there's got to be a better way than the rational zeros theorem to deal with this one, okay? And there is a little bit better way. What we're going to use to factor this is we're going to use two formulas. We're going to talk about the difference of squares first. Difference of squares says that if you have two items, let's call them A and B, they're being subtracted and they both have perfect squares, that will factor into that. Meaning that the way that you've seen this most of the time is you had something like this, x squared minus 16. X squared minus 16 is factorable because you can take the square root of x squared and you're going to get x. That's going to be the first term for your A. One of them's minus, one of them's plus. It doesn't matter which way you do this. What's square root of 16? Square root of 16 is 4. This factors into this, and you could easily multiply that back out to verify it. That's a given formula, okay? That's going to work every single time. Now we can apply that to stuff bigger than squared because all this formula states is if I can take the square root of both parts of this, then I can use this formula. Meaning, what happens if you take the square root of x to the 6th? You split the power in half, and that has a x to the 3rd. What is the square root of 4096? And that one I do expect you to plug in. So that's 64. So it passed the test. There's a subtraction symbol between these two things. Both of them have a square root. So I know off the bat that this is going to factor into x to the 3rd minus 64 and x to the 3rd plus 64. Which still doesn't seem like it helps us very much, right? Because we're trying to factor all the way down to linear parts or even down to quadratics, because of quadratics I can use the quadratic formula. That's where there's another formula that comes in handy. And it's actually a set of two. It's called the difference and sum of cubes. And what this one states is that if I have two terms, and I'm going to do the plus one first, okay? And I can take the square root of them, I'm sorry, the cubed root of them, then I can do this and factor it. This is going to be a plus b, a squared minus a times b plus b squared. And I promise you that we taught this back in Math 3. Probably maybe kind of ringing a bell, maybe a little bit. I don't expect you to necessarily have this memorized right off the top of your head right now today, but it's one, I'll send a video out for you to review on it this afternoon. It's one that's going to come in handy for factoring some of these weird ones. This was when they were summed. There was also one for when they were subtracted or they were a difference. And the variables ended up in the same places. Does anybody remember how we determined the signs in between them? Because the signs are what switched. And the way that you do this is you always use SOAP when you factor this. Because what happens here, this one was the sum. The first operation was the same. Since this one was plus, this one was plus. The O stands for opposite. The next sign is opposite. The AP stands for what to do here because that's always positive. So you can memorize this really as one formula if you remember SOAP. Because when you do the signs are, well, this one has to be the same. This one has to be opposite. And the last one is always positive. That's how we're going to factor these, because what happens with this is we end up with a quadratic. And once we at least get down to a quadratic, then we can factor that thing using the quadratic formula to find the other imaginary roots. Because one thing I didn't address when we looked at the graph, it only has two roots that we can see by looking at the graph. It only crosses twice. So that means because it's a power of 6 polynomial, it's a 6th degree, we know that it has to have 4 complex roots, which is what makes this one tougher. When there's only 2, you know you could at least whittle it down to a quadratic easily, like we did with the first one, and find its solutions. When you have more than 2, 4, 6, something like that, this gets a little tougher where you're going to need some special factoring formulas. So let's go ahead and factor this. So let's look at this. They're the same numbers. So when we go through and we do this, what is the cubed root of x to the third? And what you always do is you always take the power and divide it by whatever this number is. So 3 divided by 3 means that's x. And then you need the cubed root of 64. Is there a cubed root button on the calculator? You always just use fractions. So 64 to the 1/3 will get this done. And this is 4, because 4 times 4 times 4 is 64. So what that means, let's follow our formula here when we factor this. This one is going to turn into x minus 4. And then it's going to leave us a quadratic that we'll have to deal with. So this said the first thing squared, so we had x, so this is going to be x squared. And we're minus, so we're down here. So the next thing's plus. And x times 4, which is 4x. And then 4 squared is 16. And remember, the last one is always positive. So this factors into these two things. And we've actually found one of the roots that we saw on the graph. We see the positive 4 here. Now we need to do the same thing here. This is x plus 4 this time because those are being added. And we're still going to get these same numbers, 4x and 16, but the signs are going to be different. Remember, these are opposites, so this one will be minus, and this last one's always positive. So we knew that we were hunting 6 roots. We've already found 2. because this one says that one of the roots is x equals 4. The other one is x equals -4. Those are the two easy ones that we found on the graph when we looked at it. Now we need to take each one of these things and plug it in the quadratic formula and find those two imaginary roots that come out of each one. So this is -b, so that's -4 plus or minus 4 squared, that's 16, minus 4 times 16 times 1. Sorry, let me put the 1 in there. I skipped the 1, I apologize. 1 times 16, there you go. And then 2 times 1. So now we just need to simplify. So 16 minus 4 times 16. So that's going to be negative. And 3 times 16 is 48. So we get -4. Let me give us a little bit more space. -4 plus or minus the square root of -48 over 2. So that means we have to deal with this square root of -48 stuff. Square root of -48. So we know how to get rid of the negative. That means there's going to be an I in front. And now we need to dissect the 48 and hunt for perfect squares. So I know 48 is a factor of 16. 48 divided by 16 is 3, right? So let me actually write the whole thing out so we see it. -1, 16, and 3. Those are the three things that multiply together to give me -48. So that's square root of -1, square root of 16, and the square root of 3. This is the I. I'm going to flip-flop their sides because you want to put the number before the I. That's 4. Then you put the square root of 3. So that square root simplifies into 4i root 3. So I'm going to write this over here. So this is let's write it down a little lower. -4 plus or minus 4i root 3 over 2. Now, the reason we had to factor that out is now it has a common factor. What is the common factor between all of these real coefficients? They're all factors of 2. So this root finally turns into, write it over here, -2 plus or minus 2i root 3. That's what this x equals. And remember, that's 2 zeros for that polynomial. We're almost there. We've got to do the same thing we just did with this one. And it's going to be with this type of problem, it's got this difference of squares and then sum and difference of cubes. You get this same looking quadratic out of it. The only difference is this 4 is negative. So let's write this down and see. Instead of being -4 in the front, this is +4 because -4 is positive. We're going to get 16 minus 4 times 1 times 16 all over 2. So that's 4 plus or minus the square root of -48 again, because all these numbers are the same, over 2. What's the only difference? This one is just not going to have a negative in front when you write it out. This is going to turn into, because the square root of -48 is going to simplify the same. You're still going to have the same common factor like we did down here. The only thing is this 4 is not negative, it's positive. So we're going to get the same root, same pair of roots, but same looking root. It's just going to be a +2. So that's another 2 roots. So we found one root here, one root here, 2 in each of the imaginary things that we found. So we found all 6. So let's go through and actually list out our answers. So x equals, it was +4 and -4. And I'm going to separate these. So it's -2 plus 2i root 3, -2 minus 2i root 3. Then the other one was +2. You separate that plus or minus symbol, that's where you see both those roots. And those are all 6 roots that we can use to get us down to our factored form. So we know this one's going to give us x minus 4. We know this one's going to give us the x plus 4 when we set it equal to 0. Those two are pretty easy. We've done a bunch of those. Let me make that a little neater. These imaginary ones that we have to deal with might be a little bit tougher, and you might want to write them out again just to be sure. So this is x equals -2 plus 2i root 3. We want to set this thing equal to 0, okay? 2i root 3, you got to think of it, it's like one block that you can move around on either side of the equal sign by changing its signs. So we're going to move the 2 by adding it. And that means when this goes to the other side, it gains a negative sign. So we get x plus 2 minus 2i root 3. And this is what that root is. And then we're going to follow the same process, just like we did for these, right? Because we said, hey, this is x equals 4. This is why this went in there. This was x equals -4. That's why those went in here. We're doing the same thing, making one side equal to 0, so we can find what's actually supposed to go back inside the parentheses. So this one is -2 minus 2i root 3. So we're going to add the 2, and we're going to add the 2i this time. That makes that 0. So that's our factored form of this. I'm going to follow the same pattern for these. Only difference is to get this 2 over, it's going to be a minus this time instead of a plus. Let's actually write it out. So -2 minus 2i root 3. That's what's inside the parentheses. And last one. So this is going to be -2 plus 2i root 3. And all of those are different. They all have one sign different with each other. And lo and behold, there it is. It's a lot going on there, okay? Because even more, if you think about it, this takes us back to where we started way in the beginning. We started talking about graphs of polynomials and how it related to their factored form. When we look at this graph, and we think about a sign chart or whatever, this is the only thing that we actually see on the graph, even though all this stuff is right here. Now, if I asked you what this is in standard form, what would you have to do? We'd have to go back to like what we did right here, and we'd have to draw all those boxes with all those crazy square roots and everything and multiply everything out, right? But guess what? If you actually did it all, and no, I'm not going to do it all on this one today because it is rather large, but maybe we'll pick a smaller one and I'll do it in a video for you tomorrow. But if you took the time, draw all your boxes, multiplied all your conjugates out, this will take you back to what we started with. Whenever you go back to standard form from factored form, all the imaginary stuff disappears every time. Okay, and that's also one of the ways that you can tell when you do a problem like we started with that has imaginary roots in it. When you get down to your answer, if you still have an I in there, you've made a mistake somewhere. because that I, because of the conjugates, is always going to end up canceling out and disappearing. All right, last thing. Last question. I left it at the end. Kind of a summation of Descartes' rule of signs. And we talked about this a little bit on Monday. So remember, Descartes' rule of signs talks about how many positive, negative zeros, right? But it also, even though it wasn't directly stated, Descartes' rule of signs talks about the positive, negative, and the complex. We just didn't understand the complex yet, but that was what the -2 thing did. So let's do the positive zeros first. So this is positive, 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 and negative. How many sign changes? Positive to positive, no. Positive to positive, no. No. Positive to negative. So that's 1. And when we learned this rule, we said, hey, there's no or for this because you can't subtract 2 from 1. That's subtracting 2. We were taking away the possibility of complex roots, even though we didn't understand what complex roots were yet. Now let's do the negative zeros. Now when we do negative zeros, what's happening is we're making this negative, okay? And what it does is it makes the x negative in each one of these things. So this is what we're doing. We're using this substitution in. We're changing all those x's to negatives. And we still want to figure out the overall sign of this thing. I don't care about the actual number. I just want to know whether it's going to be positive or negative each term. This comes down to the powers again. Any even power, you can't change the sign on. Meaning negative x to the 4th is going to still be positive because anything to a even power always results in a positive answer. But this is to an odd power. Odd powers you can change the sign on. So since this one was positive up here, it changes to a negative. This one's even, so I can't change the sign. Even though it's not written, 1 is odd. That means this will change the sign. You can't change the sign of 8. 8's just 8. Or negative 8's just negative 8. Now if we count sign changes, we have 1, 2, 3. So negative zeros for this one were 3 or 1. And what we're doing when we subtract that 2 from it is we're saying there's a possibility this polynomial has some complex roots to it that we can't see actually cross the x-axis. And we've already factored this when we know it has complex roots. So what I want to get at with this is when you make this list, positive, negative, and complex. We're counting how many of each type are possible when we hunt for this. Now, positive is 1. Now we have 2 options for negative. So let's start with the 3. If one of our zeros is positive and 3 are negative, how many are left for complex? How many should this have overall? Because this is a power of 4, that's its largest, or that's the largest power. So that means its degree is 4th. That means it has to have 4 zeros. So I just have to make sure they're all accounted for in this list. So 1 and 3 adds to 4. So if this is what I see on my graph, I know right away that it has no complex roots. But I need to go through every possible combination. There's only one possibility for positive, but I could also end up with 1 negative. 1 plus 1 is only 2. That leaves me 2 for complex, meaning that this is the stuff that we focus on because these are the things that we can see on the actual graph. That's actually counting how many times I should see the graph cross the x-axis. When we went and graphed this one, what we saw is we saw that it crossed 1 on either side. And that's how we knew that it had to have 2 complex zeros because there were 2 left over somewhere. If I don't see them cross the x-axis in the graph, then that guarantees that they're going to be complex.